Lesson 6.2, comparing data sets, box plots, measures of central tendency, and standard deviation. These are all known as statistical methods. And statistics is a way to analyze data. So statistical methods are methods that have been developed to analyze data in order to make decisions. We have a lot of tools for analyzing data. A lot of them require advanced statistics courses to use and comprehend, and we're not going to get into those. The methods we're going to discuss are some of the most basic methods that can be employed. These include box plots, measures of central tendency, which are mean, median, and mode, and standard deviation. And this will help create a way to analyze data and make conclusions. Okay, so the first one we're going to talk about is a box plot, and this is a pictorial representation of the data. It's somewhat graph-like, and each section of a box plot contains 25% of the data. So the central tendency refers to the middle value or the typical value of a data, and this is measured using mean, median, or mode. The mean is the average of the data. So for example, if we have 2, 3, 5, 6, 3, 4, and 1, to find the average, we add those together. And we divide that by the total number of numbers. So we have 1, 2, 3, 4, 5, 6, 7 numbers. So we'll divide by 7. So we get 24 divided by 7. And so our average or mean is 3.43. The median is the middle value of a data set. So first let me write step 1 for mean is to add the values. And then step 2 is to divide by the number of values. Well, to find the median, step 1 is to write the numbers in order. So 1, 2, and I usually cross them out as I'm going, 3, 3, and 5 and 6. Oops, I forgot the 4. Hold on. 4 and 5 and 6. The median is the middle value, so quite literally, we find the number in the middle. So I have, if I move the same number of spaces in, here's my middle number, that's the median. The mode is the value that occurs most often. 3 occurs twice, so mode would be 3 in this set. Okay, in order to calculate the mean, median, mode, we just did a brief one, but I'm going to go over this in more detail. So step 1, add the numbers. Okay, so I'm going to do 20 plus 11 plus 10 plus 19 plus 12 plus 15 plus 11 plus 19 plus 19 plus 18. This gives me a total of 143. Step 2 is divide by the number of numbers added. So I added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So I'll take 143 and divide it by 10, and I'm going to get 14.3 for my mean. The median is the middle value of the set. So step 1 is to put the numbers in order. So I start with the smallest number, that's 10. And then I have 2 11s. I have a 12. Then a 15. Then an 18. I have 3 19s. And a 20. Step 2 is to find the middle. Well, if I go starting on each end and I just start moving in towards the middle is right here. Okay, if this is a number, the middle lands on an actual number, this is the median. If a space then we add the two numbers to either side. And divide by 2. In this case, we found a space. So I'm going to take 15 plus 18. So 15 plus 18 is 33. And then I divide that by 2. And so my median would be 16.5. That's the middle of this data set. And mode is the most frequently occurring number or numbers in a set of numbers. If more than one number occurs the same amount of time, and then you can have more than one mode. In this case, we have a 19 that occurs 3 times, so our mode is 19. Okay, next we need to be able to calculate the range, find quartiles, and what's called the interquartile range. Range is the distance between the greatest and least values in a set of numbers. Quartiles are 1/4, 1/2, and 3/4 of the way through a set of numbers. The interquartile range is the distance between the first and third quartile in a set of data. Okay, so let's take a set of numbers. We can use the same set that we had just used before. I had 2 11s. Let me go back. Hold on. I had a 12, a 15, an 18, 3 19s, and a 20. The range, you take the largest number, or the largest value, minus the smallest value. So in this case, 20 minus 10, and so my range is 10. Okay, now with the quartiles, we want the numbers in order. So first we put the numbers in order, then we find the median, which we had already done. The median occurred right here and was 16.5. Next, we find halfway through each half. So here's one half of numbers, here's the other half. Halfway is halfway through each of those. And this is quartile 1. The median is quartile 2, and this is quartile 3. These are the 1/4, 1/2, and 3/4 of the way through the set of numbers. The interquartile range is the distance between the first and third quartile in a set of data. So again, if we're using the same set of data, this was quartile 1, and this is quartile 3. So the interquartile range is 19 minus 11, which is 8. So we're going to draw a box and whisker plot for this set of data, and we'll need to find the quartiles in order to do this. So the first step we do is we put the data in numerical order. So our smallest number here is 11. I have a 12. I have another 12. 14. 14, 15, 16, 16, and 20. Again, I like to cross the numbers out or circle them as I use them so I know I didn't miss any, because if I miss any, it'll put everything out of kilter. So that was step 1. Step 2 is to find the median. So to find the median, we find halfway. Okay, so I have 1, 1, 2, 2, 3, 3, 4, 4, 5. Here's the median. Step 2. Median is 14. Then we find the first quartile, which is half of the first half. Okay. That would happen right here. And when I don't have a number, I add the 2 numbers to either side and divide by 2. In this case, it'll still be 12. Then I find the third quartile, which is half of the second half. And that will occur right here. And again, if it lands on a space, you add the 2 numbers and divide by 2. So now I've found all 3 quartiles, the first, the second, and the third. Then I create a number line that fits the scale of the data. So I need a number line that will take me at least through to 20. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And then I draw a rectangle that has Q1 and Q3 as the ends of the rectangle. So here's quartile 1 is at 12. Quartile 3 is at 16, so 12, 13, 14, 15, 16. And I make a rectangle. Okay. And I draw a line through quartile 2, which is occurring at 14. And then I draw whiskers that extend to the end points. So I thicken that number line. And this shows me, this box shows me where most of the data occurs. Then, oh, sorry, that shouldn't have gone to 10. Hold on. That should have only gone to 11. 10 wasn't one of our data sets. So that's a box and whisker plot. So we've got 2 more. So again, first we have to put the numbers in order. 31, 32, 32, 35, 35, 36, 37, 37, and 39. I find the median, so 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers, so here's my median. Then I find the halfway points, 32 and 37. Draw a number line, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. I draw a box between Q1 and Q3. So Q1 is occurring at 32, and Q3 is at 37. So I draw my rectangle. I draw a line through the halfway point, or the median. It's not actually halfway on this particular box. And then I make my whiskers. Okay, so what I would like you to do is pause the video now and draw your own box and whisker plot for this data set. And then once you've finished drawing that one, come back and check your work and see how you've done. Okay, your picture should look somewhat like mine, with your quartiles at 22, 24, and 26. And again, this box shows us where the majority of the data lies. Okay, data can be symmetrical or asymmetrical. Symmetrical is having the same shape on either side of the middle or the median. Asymmetrical means having a different shape on either side of the middle. So symmetrical examples look like this, where your data is pretty much the same on both sides. And asymmetrical looks like this, where your data is not the same. So as you can see, if our data is a curve, we have an even curve on both sides, our boxes are the same size, and our whiskers are the same size, or our bars are about the same size. Here we have a curve that's not the same side on each side of the middle. Here's the middle here. We have a box that's definitely not symmetrical, and bar graph that's not symmetrical. Data can be asymmetrical for a lot of reasons, but one of the most obvious reasons is because of what's called an outlier. And this is a data point that is drastically different from the normal set of data. So for example, if most of the people taking a test in a class are scoring 70 to 75, and you have somebody that scores a 3, that would be an outlier. Oh, here's another example. We've got a bunch of test scores in the 70 and 90s, and you have a 52, and 52 is the outlier because it's very different than the other scores. And our box plot would look like this. So as you can see, we're not symmetrical. This whisker is much longer than that whisker, and our quartiles aren't the same size. There's our outlier. Okay. If we want to determine if a data point or points is an outlier, we can perform a calculation to ensure that it is. So here's our test example. So first we calculate the interquartile range. So in order to do that, we first have to put the numbers in order. So step 1 is numbers in order. So our lowest number is 52. Then we have a 73, a 75, 78, and 83, and 86, and 88, and 89, 90, 92, and 95. Next, we find our median. Okay, so we come 5 in from that side and 5 on this side. Our median is 86. And then we'll find the middle of each of the other sets. So here's quartile 1, quartile 2, and quartile 3. Our interquartile range is Q3 minus Q1. So that's 90 minus 75, which is 15. Now we multiply the IQR by 1.5. So I'm going to take 15 times 1.5. And I get 22.5. Okay. If I take Q3 plus this number I got here, 22.5, that'll give me 90 plus 22.5. 90 plus 22.5 is 112.5. Any number greater than this would be an outlier. Or if I take 22.5 and I subtract it from Q1, so in this case 75 minus 22.5, well 75 minus 22.5 is 52.5. Any number less than 52.5 is an outlier. Since 52 is less than that, 52 is an outlier. Okay, determining what number or data points are the best measure of the central tendency of data. If your data is symmetrical, then the mean is the best representation of the center, and again, the mean is the average. If your data is asymmetrical, then the median is the best representation of the center, and this is again the middle number. Okay, so we're going to make a box plot for each of these distributions. So algebra goes from 40 to 100. I need to see how many numbers I have here, and I'm going to find my median. And rather than count, I just mark them off until I get to a point where I've reached the middle. So I lost track. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so my median is going to be right here. So I'm going to take 80 plus 81 and divide it by 2, and I'm going to get 80.5. Then I'm going to find the middle of this set of data. I have 3. I'll just do this. Okay. So my quartile 1 is going to be 70, right over here, plus 75 divided by 2, which is going to give me 145 divided by 2, which is going to give me 72.5. My next quartile is going to be 92. So those are my ranges for Algebra 1. Next, I'm going to look at geometry. I have the same number of numbers, so my middles are going to be in the same spots. Here I'm going to have an 85. Here I'll have a 91 because 91 is halfway between 90 and 92. And then for this one, I'm going to have to add 75 plus 78 and divide by 2. 75 plus 78 is 153. Divided by 2 gives me 76.5. So I need to make a box plot of the data, and I need to go between 40 and 100. So 40, 41, 42, 43, 44, 6, 7, 8, 9, 10. Hold on a second. Okay, I just made some number lines really quickly. I'm going to go ahead and graph algebra in blue, and I have a 72 and a half. So here's 71, 72 and a half, roughly. And I have a 92. And I draw my box. And then my highest score, my median is 80 and a half. My highest score is 100. My lowest score is 40. And I go ahead and create my whiskers. And that's algebra. And then for geometry, I go between 65. Oh, no, sorry. Messed that up. 76.5 to 91. My median occurs at 85. My highest score is 99. And my lowest score is 65. And that's geometry. So I've made my box plots. Now we want to see which one had the largest interquartile range. So if we go back, we've got 72 and a half, 92 and 80 and a half. So right here we had 72.5. We had 80.5 and 92. Then on this side we had 85, 91, and 76.5. So for algebra, we'll do 92 minus 72.5, and we're going to get 19.5. For geometry, we'll do 91 minus 76.5. We'll have 14.5. So algebra has the largest IQR. Remember, IQR is interquartile range. The highest median, again, we'll need to bring over our data. So we had 72.5, 80.5, and 92. We had 76.5, 85, and 91. 85 is a higher median, so that's geometry. Okay, now without making any calculations, we need to see, do any of the data points look like outliers? Well, to me, this 40 looks like an outlier. None of the other ones really come across as major outliers, but we've got to calculate that to see if we can identify them. So we've already calculated algebra IQR, and we've already calculated geometry's IQR. Algebra's was 19.5 and geometry's was 14.5. Now we're going to take the IQR and multiply it by 1.5. So 19.5 times 1.5 is 29.25. Geometry, I'll take that 14.5 and I multiply it by 1.5. And I get 21.75. Now to determine if we actually have any outliers, I again need to bring back my Q1s and my Q3s. Here I had 72.5 and 76.5, and here I had 92 and 91. So I'm going to take 72.5 and subtract 29.25 from it, and I get 43.25. This is lower, so it is an outlier. If I take 92 and I add 29.25 to it, I get 121.25, so I have no upper outliers. For geometry, I'll take the 76.5 and I subtract 21.75. And I'll get 54.75, so I have no outliers there. And then if I take the 91 and I add 21.75, I'll get 112.75. So I have no outliers in geometry. And I have 1, which is the 40 in algebra. Okay, looking at the box plots. So let's go back and look at the box plots really quickly. Hold on. So here are our box plots, and we want to say, looking at the box plots, which one do we think has the higher average? Well, looking at this box versus this box, as you can see, the box in geometry is shifted slightly more to the high side than algebra, so we can assume or guess that algebra is the lower average. So we'll go ahead and say algebra, but then we can calculate the means to determine which is higher. So I'm going to add all of these numbers and all of these numbers, and then I'll divide by the number of numbers I add. Okay, so I'll have the sum for algebra and the sum for geometry, and then I'll divide by the number of numbers. So I'm going to do that really quickly. I'm just going to go down the list and add that. My algebra sum is 1605. Now for geometry, my sum is 1668. Now we need to count how many numbers did we add. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 numbers. So I divide each of these by 20. And algebra gives me an average or mean of 80.25. And geometry gives me an average of 83.4. So geometry is, oh, you know what? I wrote algebra for highest. I meant to say geometry. We were saying algebra was lowest. I wrote the wrong thing. Geometry is highest. Okay, now we have things called the mean absolute deviation and the standard deviation. And a deviation is just different than the norm. Okay, the mean absolute deviation is the average of the distances of each value from their average. So that sounds kind of weird, right? The mean of the distances of each value from their mean is the average of the distances of each value from their average. And this tells us how far each value is from the middle. It's kind of a spread. So how far does the data spread away from the middle of the data set? We calculate using the following formula. MAD, being the mean absolute deviation, is equal to the sum of the absolute value of the numbers minus their average divided by the number of numbers. So E is the sum of the absolute values. That's the symbol for sum in math. X is a data point. X with a bar over it is the average of all of the data points. And N is the total number of data points. So how do we find this? Well, we've got some test scores. First, we're going to find the average of the test scores. So I'm going to add these all up. Okay, so my sum here is 985, and then I need to divide that by how many numbers I added. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. So I divide that by 12, and I get 82.08. That's my average of the test scores. That's X. Step 2 is I subtract the average from each test score. So this might take a second, but I do 78 minus 82.08, 86 minus 82.08, 85 minus 82.08, 79 minus 82.08, 77 minus 82.08, 83 minus 82.08, 92 minus 82.08, 99 minus 82.08, 95 minus 82.08, 73 minus 82.08, 56 minus 82.08, and 82 minus 82.08. So I'm going to go through and do all of this subtraction. I'm actually going to pause the video while I do that, so the answers are just going to magically appear in a moment. And there they are, magically appearing. So now I have all of the subtraction, and I'm going to add the absolute values of all these numbers. That means all numbers are positive. So anything that's negative, like this negative 4.08, we just make it positive. That should be 0.8 plus 0.92. Okay, and this will equal 95. And now I need to take that number and divide by the number of test scores. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 test scores. So I divide by 12. And I get 7.916. 6 repeating, or 7.9. And this is about, on average, how far any data set is from the middle. Standard deviation is a measure of how spread out the numbers in a data set are. It's symboled by the Greek letter sigma, and it has the following formula. And it's very similar to the MAD, but the difference is we don't have absolute value, and we're taking a square root. Again, this kind of E is the sum, X is each value in the data set, X with a bar over it is the average of the numbers in the set, and N is the number of numbers in the set. The standard deviation gives us values that help us determine which numbers are normal and how far from normal other numbers are. Okay, so we have waiting time in minutes of several people at the DMV. Oops. So what we want to do first is very similar to finding the MAD. We want to find the average, X bar. So we add the numbers and divide by the number of numbers. So I'll have 11 plus 7 plus 14 plus 2 plus 8 plus 13 plus 3 plus 6 plus 10 plus 3 plus 8 plus 4 plus 8 plus 4 plus 7, which gives me 108. And then I need to divide that by the number of numbers. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers. So I divide by 15, and that gives me 7.2. Okay. All right, the next thing we want to do is we find all of the differences. Hold on. Realized I left something off of this. There needs to be a squared here. I left that off accidentally. Sorry about that. So we find all of the differences between our data set and the average and square those. And then add them together. So what I'm going to be doing, I'm going to write this out this way. I'm going to do 11 minus 7.2 squared plus 7 minus 7.2 squared plus 14 minus 7.2 squared plus 2 minus 7.2 squared plus 8 minus 7.2 squared plus 13 minus 7.2 squared plus 3 minus 7.2 squared plus 6 minus 7.2 squared plus 10 minus 7.2 squared plus 3 minus 7.2 squared plus 8 minus 7.2 squared plus 4 minus 7.2 squared plus 8 minus 7.2 squared plus 4 minus 7.2 squared plus 7 minus 7.2 squared. And the reason I put that space in there is to give me room to actually work these out. And I'll do 11 minus 7.2, and that's going to give me 3.8. So I have 3.8 squared plus 7 minus 7.2 is negative 0.2 plus 14 minus 7.2 is 6.8 squared. 2 minus 7.2 is negative 5.2. 8 minus 7.2 is 0.8. 13 minus 7.2 is 5.8. 3 minus 7.2 is negative 4.2. 6 minus 7.2 is negative 1.2. 10 minus 7.2 is 2.8. 3 minus 7.2 is negative 4.2. 8 minus 7.2 is 0.8. 4 minus 7.2 is negative 3.2. I just did an 8 minus 7.2, and I just did a 4 minus 7.2, so I'll rewrite those. And then 7 minus 7.2 is negative 0.2. Now I'm going to go through and I'm going to square each of them. So 3.8 squared is 14.44. Negative 0.2 squared, it's a negative times a negative, so that's a positive 0.04. 6.8 squared is 46.24. 5.2, negative 5.2 squared, again, negative times a negative. These will all be positive when you square them. So I'm just going through and I'm squaring everything. Should probably write this closer to where I was. And again, like I said, I'm just going through and squaring all of these. 7.8 squared, 4.2 negative, 17.64, 0.8 squared, negative 3.2 squared, and then negative 0.2 squared. Now I've got all my squares. These are the numbers I add. So 14.44 plus 0.04 plus 46.24 plus 27.04 plus 0.64 plus 33.64 plus 17.64 plus 1.44 plus 60.84 plus 17.64 plus 0.64 plus 10.24 plus 0.64 plus 10.24 plus 0.04. And I get a sum of 241.4. Once I've got that sum, I divide by the number of numbers. Okay, so I'm going to take 241.4 and divide it by 15. And I get 16.09. And then finally, I take the square root of it. So the square root of 16.09 is 4.01. And this is my standard deviation. Basically what that says is anything within 4 minutes of the center is a normal wait time. Anything outside of that is either really long or really short. That's basically what standard deviation tells us. Now what I would like you to do is to try to work out the standard deviation of this set of numbers. It's a smaller set, and it's the prices of cordless phones at an electronics store. And I want you to interpret it like I just did. So I'm going to pause the video, and I would like you to work this out, and then once you've taken the time to work it out, come back on and see what you get as your standard deviation, and we'll compare. Okay, so now that we've calculated the standard deviation, I got a standard deviation of 13.99. The average is 60.71. So basically, if you're paying more than $14 off of 60, or that's paying too much. And if you're paying less, like so more than $14 less, then you're getting a really good deal, because that's 14 more than, that's out of the norm. That's what the standard deviation is telling us.